what is the goal of digital communication? Okay. So can anyone tell me what do we want to achieve by digital communications? Okay, what is the point? What is the goal of a communication system? Please feel free to speak.
Effectively transmit the message from this transmitter to receiver.
Yes. Okay. So what you are telling is essentially send information from one point in space to another. Okay. So this is one way of thinking about digital communication. So transmitting information from one physical location to another physical location is one way of sending information. Actually, digital communication a little bit more. You can also think of information being transmitted in the same place across time. For example, if you have a hard drive, you're storing your information in the hard drive and retrieving it at some other point in time. Okay, so it's no need of being just space. You can also say space and time. Okay? Both of them digital communication deals with. Okay, so the goal of digital communication is to send information reliably. Just not only sending information, but you have to send it in a way so that it can be you can be 100% sure that the same information that you want. Okay, so reliable transfer of information from one point in either space or time to another. Okay, so generally when we think about cellular systems and other things, we talk about transmitting information across space because different locations you want to transmit information. But there are certain groups, for example, storage on your hard drive, storage on your SSD drives, which talk about transmission of information in time. Okay, but anyway, we'll not worry about that. I'm just telling you that's also one thing. Okay, so the question is, how do we do this? Okay, so what I'm going to now do is I'm going to draw a very, very high level block diagram of what is going to be there in a communication system. Okay, so this block diagram comes from this seminal work of Dr. Shannon. I hope most of you know who Shannon is. Most of you must have heard of Shannon's theorem. So this block diagram has a lot of deep meaning to it. So I'm just going to draw that and then let's discuss from that point. Okay. So you have some message that you want to transmit. You map that into bits. Okay, you map that into some bits. Bits means 0, 1. Okay, bits are 0 and 1. Okay, you map it a sequence of bits. Then you take these bits and let's pass it through you pass it through something called as a modulator. I will go into depth with this modulator later, but first you pass something to modulator. So essentially, modulator, what does it do? It takes your bits, which are still logical zeros and ones. They don't mean anything in terms of electricity or voltages or currents. They're just zeros and ones logically. Then this modulator converts this into electrical signals, which you pass it through your medium. Okay, the medium is generally called as channel. Okay, for example, this can be a wired medium, this can be a wireless medium, this can be a magnetic tape medium. Whatever it is, we just call it a channel. Okay. So on the receiver side, what do? You have something called a demodulator. Okay. Demodulator gives out bits. So the bits are again converted back to messages. Okay. So if I call the message that you're transmitting as M and the message you're receiving as M hat, the goal of digital communication is to make sure that M is equal to M hat. Okay, most of the times. okay, as reliable as possible. Okay. So this is a very, very high level block diagram. So now what I'm going to do is I'm going to go in depth on this modulator, channel and other things. We'll just go and then we'll discuss things. Okay. So are there any questions at this point? It's very simple. So this is a digital communication system. If it was an analog communication system, you will not have bits there. You would have taken your message and put directly into your modulator, and you would have received the message. Okay. So in an analog communication system, you do not talk about transmitted message being equal to the received message, because they'll never be the same. Okay. Whereas in a digital communication system, you can say that M is equal to M hat. The messages are discrete. Okay. So now, so suppose you have you map your messages to bits. So we'll start at the bit level. So your bits are your messages from now on. It has zeros and ones, a long sequence of zeros and ones. Then the first thing that you will do is you will want to compress bits. Okay, you want to compress them so that you don't transmit too much information. Okay. So I'm going to write this model, but generally they won't put this model. You say, I mean, essentially it's called a compression. Okay. So after compression, what you do is you add something called error control codes, FEC. So we understood what is compression. What does compression do? I mean, all of us have used zip kind of compressions most of the times. We also looked at MP3 compression and other things. Okay. So compression, what does it do? Compression removes redundancy in your bit sequence. Okay, so you have a long set of bit sequence. What does compression do? Compression tries to reduce the redundancy and tries to decrease the amount of information that you transmit. Okay. So that is what compression is. What does error control code do? So when we transmit information in a channel, okay, so when we transmit information, suppose we transmit information in a channel, we're transmitting 1. Okay, so that output of the demodulator and other things, you again get back bits. So there's a probability that this one might be 1, or the 1 might get flipped to 0. Okay, similarly, when you transmit 0, there's a probability that 0 is still retained as 0. And you can flip over as 1. Okay, there's some probabilities. Okay, that's what I mean. Channel introduces noise. We're going to look at that in a minute. So because of this impairments and other things, what happens? Your information is going to get corrupted. Okay, so the job of error control code is to make sure that you can recover even if there are errors in the channel decoding. Okay, so for example, one of the most simplest error control code is called the repetition code. Okay. What this means is, see. So let's take a simple example. Okay. Suppose the probability of 1 going to 1 being 1. This is the TX, this is the RX, is 0.9. So at 90% of the time you will get 1 as 1. 10% of the time 1 becomes 0. Similarly, 0 becomes 1 10% of the time. And 90% of the time 0 becomes 0. 0 still remains as 0. Okay. So suppose I want to transmit 1 bit of information, which is 1. So, I mean, example, repetition code, just I'm going to give you this an example. Suppose only 1 bit of information you want to transmit is to be transmitted. Okay. So suppose, and that by bit of information, let's assume is 1. So if I transmit 1, what is my probability of error? Can anyone tell me? What is my probability of error? It will be 0.1, correct? Okay. So instead of that, what I'm going to do is, I'm going to transmit 1 3 times. If I have to transmit 1, I will transmit 3 times. If I have to transmit 0, I will transmit 3 times. Okay. And the receiver, what will I do? I will look at something called majority decoding. Essentially, I look at the number of ones I obtain. If the number of ones is more than 2, if the number of ones is more than 2, I declare it as 1. If the number of zeros is more than 2, I will declare it as 0. Suppose I do that. Can anyone tell me what may probability of error be? Will it be at least less than 0.1?
0.001.
It will be of the order of 0.00. It's not exactly 0.001. It will be less than 0.001. Okay. So essentially, it's easier to compute probability of correct detection. Okay. So in this case, okay, let me just write. So it's very obvious that in this case, your probability of error in this particular case will be less than or equal to 0.001. Okay. So I will tell the math of this later. I'll give it as a homework problem. We can play this as a homework problem. It's very interesting. Okay. We'll look at this later. Okay. So this is simple repetition code. It turns out that repetition code is not optimal. There are much better codes which provide the same reliability with lower number of redundancy. For example, in this repetition code, what did you do? You transmitted the same one thrice. Okay, so you are not transmitting additional information. Your information is still 1 bit, but you are using the channel 3 times, which is a waste of the channel. Okay, so this increases redundancy. Okay, that's what you should keep in mind. So this is also called FEC, forward error correction code. FEC. Okay. So okay, let's just go across the block now. Let's see what are the other things. I'm just going to erase this so that we can. Okay. So after FEC code, so again you get bits. Still we're in the bit domain. This is all still in the 0. FEC code output also is bits. Then what you do is you do mapping, modulation. Right? Essentially, this is a constellation mapping. Okay. So what is a constellation map? We'll go and get to the constellation in a minute, but what is a constellation map? This is the first time in which you convert your zeros and ones to electrical signals. Essentially, effectively, you convert your zeros and ones to real numbers. Okay. A simple constellation that most of you know is QPSK or BPSK. Let's take BPSK. Okay, let's take BPSK. In BPSK, what do? You map 0 to -1 voltage and 1 bit 1 to some plus voltage. Yeah, I'm just giving a 1 and -1, but you can, instead of that, you can say it maps to plus A minus A. Plus A minus A. Okay. So 0 is mapped to plus A and 1 is mapped to minus A. Okay. So similarly, there are multiple other constellations. BPSK is one. You have 4 QAM. You have 16 QAM. So many constellations are there. I'm just giving some examples. Okay, we will see these things in a little bit. So this is what constellation does. So after constellation, okay. So okay, so let's also do 4 QAM so that it's. I want to tell you something else. If you look at 4 QAM, okay, there are 4 points in the constellation. Okay, so these points generally are 1 by square root 2, 1 by square root 2. Plus 1 by square root 2 minus 1 by square root 2. This is minus 1 by square root 2. So the reason I'm putting 1 by square root 2, 1 by square root 2 is that the energy in this constellation is 1. Okay, so there are 4 points in this constellation. Okay, these are the 4 points in the constellation. Okay. So what you do some mapping. You map from 0. The bits you get. So each point can represent, since there are 4 points, each point can represent 2 bits. So for example, you can map when you get 0, 0 is bits. You map 0, 0 here, maybe 0, 1 here, 1, 0 here, maybe 1, 1 here. This is not an optimal mapping, but just I'm giving you an example of that mapping. Okay. So in this case, you see that the outputs are two voltages. One is the in-phase voltage and one is the quadrature wave. These are two dimensions, no? 1 by square root 2 and 1 minus 1. I mean, so for example, if you get 0, 0 bits, here there is a sequence of bits. The sequence of bits coming, you pick out 2 bits and map it to this. Okay. You output 1 by square root 2 and 1 by square root 2. Okay. So this is called, the x-axis thing is called the in-phase and the y-axis is called the quadrature phase. Okay. So essentially you get two wires which are out, two wires out. Okay. One is called in-phase and the quadrature phase. So I also represent this as a complex number. So I say the output is equal to x plus iy. Okay. X will be the in-phase and y will be the out of phase. I mean quadrature phase. Okay. So essentially the output is a complex number. Is it clear? Why it's why? So the complex number is one way of representing it. I mean that's one way of thinking about the whole thing. Right? So you get I comma q. Ashok sir, please.
So if you can explain this under root 2, why under root 2, why not under root 3 or something else?
Okay. So essentially that's a good question. Let me, I mean, it's actually better to clarify this, no? So I'm going to say, so I'm going to call this point as S1, this point as S2, this point as S3, this point as S4. Okay. So if I call this S1, S2, S3, S4, let's compute the energy in the constellation. Okay. So how do I find, if I give you a complex number, what is energy in the complex number? The energy in the complex number is the magnitude square. Fine. So S1, what is the energy in S1? S1 will be 1 by square root 2 whole square plus 1 by square root 2 whole square. That is nothing but, if you think about this is the length of this whole square. Okay, so this will be half plus half, which is equal to 1. Similarly, S2 also will have, if you do compute S2, I mean, it's the same thing as 1, so on and so forth. Now, what is the total energy in the constellation? Okay, what is energy in the constellation? So if you have some points, so essentially the constellation consists of S1, S2, S3, S4, and so on and so forth. The energy in the constellation is the probability that S1 occurs into mod S1 square plus probability that S2 occurs into mod S2 square, so on up to probability that S4 occurs into mod S4 square. Okay. So if you assume that your bits are equilikely, if the bits that come out of your FEC are equilikely with probability half. So bit 0 occurs with probability half, 1 occurs with probability half. What is the probability that you get the point S1? Can anyone tell me?
25%, sir.
25%, 1/4. It will be half into half, which is 1/4. Okay. So what we have is the probability of S1 will be 1/4. The energy in S1 square that we just computed here, now this is the S1 square. The energy in the S1 square, S2 square, that's equal to 1. 1/4 into 1 plus 1/4 into 1 plus so on. Plus I'll write it 1/4 into 1 plus 1/4 into 1, which is equal to 1. Okay. So in general, what the convention is that you always try to normalize your constellation so that the average energy in the constellation is always 1. Okay. So if you take the example of BPSK, for example, let's take the example of simple BPSK. Okay. So 0 gets mapped to here, 1 gets mapped to here. So what is the energy of this? So energy of this, how do you compute? You call this as S1, you call this as S2. What is mod S1 square? Mod S1 square, this time this is not a complex number, just a real number because it's BPSK, will be 1. Similarly, mod S2 square will be also equal to 1, minus 1 whole square, which is equal to 1. Okay. What is the probability of 1 in this case?
0.5.
0.5, which is half. Similarly, probability of minus 1 is also half. So the total energy will be equal to 1. Okay. So when we go to 16 QAM and 64 QAM, I'll show you the values. It will be a little bit weird. They will have 1 by square root 3s and all those things also will be there. Okay. The main reason is to make sure that the energy is normalized to 1. Alex, please.
Sir, how we represent it physically? You told two wires are there. Is it a
Yeah.
serial data or a parallel data? Means,
It's parallel
physically,
data.
okay.
So until this point, data was serial. Zeros and ones were serial. 0, 1, 0, 1. At this point, I and Q come parallel after constellation map. Okay, you have an I stream and a Q stream. We can actually, I'm going to erase this and draw the block diagram. Any other questions before we proceed?
Yeah, so
I'm going to erase
so
this.
basically, what in physical world you are saying that if a particular point, say S1, is nothing but a amplitude and some phase. So if that is there, then you construct that as a 0, 0. Is that the case or something else?
That's correct. So essentially, up to for example, up to this point, everything is logical. It's best bits. That means nothing. They are not voltages or anything. They're just logical numbers. At this point, we're mapping bits to some real values. In this case, 1 by square root 2, 1 by square root 2, which can be thought of as voltages or currents. Okay?
So generally, these voltages are of which range, in the sense that amplitude would be how much?
So that is independent, so that we don't have to worry about. That's implementation specific. But what we have to think about them is we have to think about them that they are two real numbers. That's all. And we generally normalize the real numbers so that the energy at this point is 1. Because there's a power amplifier and other things later which scale up all these things. I will tell you that.
Okay.
Okay. So at this point, you can think of the bits are mapped to some real numbers. And in general, the bits are mapped to some complex numbers, not real numbers, but complex numbers because they're 2 dimensions of real numbers. Fine. So I'm going to just erase this and then we are going to do the next, go to the chain. So you have I and Q. Maybe I'll just draw, okay. So after I and Q, generally, there are some filters. I'm not going to put all the filters and other things for now. So after IQ, you send them to what? You send them to an IQ modulator, okay, or a quadrature modulator. Okay, so what does a quadrature modulator do? A quadrature modulator takes I. This is the I part. This is the Q part. Anyway, there are 2 separate wires that are coming. Sorry. The 2 separate wires that are coming. Then what will it do? Sorry, let's try this. So there's an oscillator. Maybe just 1 minute. Let me just draw this properly.
Sir, there are some doubts in the chat window.
Yeah, I'm just 1 minute. So is there any specific reason to normalize energy to 1? So the thing is, it will become clear when we go ahead. So essentially what they want to do, it's at least theoretically, it's a good idea to normalize to 1 because it will make your calculations of energy. For example, when you're calculating the output of your power amplifier or something, this kind of normalization will help you out in understanding how much is the output powers and other things. Okay, there's no, it's practically you do not normalize, but when we do the math and all that, it's easier to think of your constellations always normalized to 1. Even for example, your standards also will tell you to normalize to 1. Okay, why do we assume all possibilities to be equiprobable? Okay, that's a very, very good question. So what does your FEC do is, so essentially we make that assumption that the output of your FEC bits are equiprobable. Okay, that's an assumption. Actually, it's not very true, but it's very true with very, very high probability. It's true with very high probability. Okay, so the output of your compressor, if your compression is very good, will always be, the bits will be always be equiprobable. But the output of your FEC need not be equiprobable, but we generally make the assumption that they are equiprobable. The probability distribution will be very, very slightly skewed. Okay, so in general, we can assume that the bits are equiprobable. Once the bits are equiprobable, the constellation points become equiprobable because you are choosing the constellation points based on a sequence of bits. For example, 4 QAM, you choose 2 bits and get your constellation. Okay. So this is your typical quadrature modulator. Okay, where you have so this is the IQ is the baseband signal. IQ is also called the baseband signal. You may do some filtering and other things. I'm not putting all that. Then you upconvert it. You upconvert it to some center frequency. This is called upconversion. Okay. Essentially, there's a DAC and ADC also. I'm not drawing the DAC. I will just put the DAC and ADC so that it's easy for us. Okay. So the I and Q will pass through some DAC, digital to analog converter. The output of which, I said DAC means there are two DACs, one DAC for I, one DAC for Q. Okay. When I say IQ, it always means two DACs. This two DACs output will go into I and Q apps. Okay, and you do an analog upconversion, or this you can do in digital domain also. You do an analog upconversion. This is called a quadrature modulator. The output of this, you get your RF signal. Okay, so FC, for example, in Wi-Fi will be 2.4 gigahertz, and 3G it can be 3.5 gigahertz or 26 gigahertz or whatever. Okay. So this is a high-level block diagram on the transmitter chain. Fine. And at this point, you put your amplifier, you put your power amplifier, and then you put your antenna. Okay, I'm not putting the filters.
So the baseband signal is kind of a digital signal completely, right?
Yeah, baseband signal. We can see even this is called baseband signal. Okay, but generally when we say baseband signal, it implies a digital baseband signal. So baseband signal means in general zero frequency, zero IF.
Okay, so that's a kind of a mathematics where you have all those mathematical values for every set of bits. If it is say QAM 4, then all those 4 bits will become that mathematical things, and that is coming, and that will get converted into analog signal. Am I right?
Yeah, DAC will convert it into analog signal. Digital to analog converter will say essentially we saw so I and Q can be 1 by square root 2 plus 1 by square root 2. Okay, so they are still digital signals. So DAC will take those digital signals and convert to analog values, actual voltages, which will feed into the IQ modulator.
Okay. So that means those numbers will, so some algo will convert that into a number depending upon what QAM we want to use, and that number will be an input to that DAC, right?
Yes, input to the DAC. The complex number will be input to the DAC. DAC will convert that into 2 voltages, one for I, one for Q, and that will be fed. So this is called the mixer. This is the oscillator.
So when it comes to this baseband, analog kind of baseband, do we use any frequency or it is kind of a square wave, or how it is like?
It is still, it has frequency. I'll just tell you. I'll explain you that 1 minute. Okay. So if you look at the spectrum at this point, okay. So I'm just going to draw this down. So this is my frequency. This is my zero frequency. The spectrum at this point, maybe I'll put another color. The spectrum at this point will be something like this. It will be centered around 0, baseband. Okay. When you do FC, for example, if FC was 2.5 gigahertz, example 2.4 gigahertz, this whole thing, all this part, this mixer and everything does is, it will shift the frequency to same thing. It will look the same. I'm not able to draw the same thing. It will look the same, but to different frequency FC. Okay. Even the baseband signal will also have a spectrum. But the spectrum is centered around 0. In general, it's centered around 0. Okay. This is called the upconversion. This is also called upconversion. Upconversion moves it into FC.
So when you say baseband, so after DAC you have 0 frequency initially, you are saying, right? And then you draw that, and then and later on it will be shifted to the actual frequency on which it will be transmitted. Am I right? Or
that's correct. That's absolutely correct. That is what this particular thing is doing. It's taking the signal, multiplying with the oscillator sine value, sine and cosine, and then converting to the RF signal. So up to this point is zero frequency, 0 center frequency. This point onwards, it will be at 2.4 gigahertz or whatever you put as FC.
So basically, let me understand. Sorry, I would be disturbing you. So suppose I'm using a 4 QAM, and then I have two bits of information, right? So either 00 or 01 or whatever combination, and that is finally being converted as an amplitude and some phase, right?
Yes. So IQ. So you can think of.
So
Yeah.
let me complete, sir. And so
Yeah.
one after another, such bits will start coming. So it will have some frequency, right? That
Yes.
that will be pushed to.
Yes.
I mean, and then those need to be converted to the FC later on, right?
Yeah, that's what is connected to the FC. Yeah.
Okay. So initially, the center frequency is 0, and those whatever frequency we use depending upon how fast we are trying to send the data, right? Or it is something else.
So, no. So how fast we are trying to send the data is the bandwidth of the signal. So that is this. Okay. So
Okay.
DAC will have a sampling frequency.
Okay.
DAC will have a sampling frequency which determines your bandwidth. That is your bandwidth.
Okay.
Okay, it will tell. So at this point, baseband signal, there's no notion of time now. They're just digital signals coming one after another. The question is how much time is there in between them is decided by the DAC sampling frequency. That will determine your bandwidth. Okay. And the center frequency is determined by this. The center frequency is determined by this FC.
So if it is faster, that means sampling rate has to be very, very high, and so that means bandwidth will be higher and time will be less, right?
Yeah, exactly. Bandwidth will be higher, so the distance, the time between the samples will become less.
Yeah. Okay.
So let's just go forward. Okay, I'm just going to erase this a bit. Okay, so this is the transmitter chain. How will the receiver chain look? The receiver chain will look exactly the opposite. We have the antenna, we have the low noise amplifier. Then the same signal will go into essentially get multiplied.
Can I just interrupt again? Sorry. So from a baseband signal which is centered around 0 frequency and then converting into a other frequency. So how that is done? Is there any?
So that is done through this mixer.
Pardon?
That is done through this mixer. Okay.
Okay.
So we can have a separate conversation where I can tell you about this part.
Actually, sir, this is what basically the concept of the modulation, that baseband frequency is converted to a higher frequency.
Yeah. So this is called IQ modulator. This is also called as an IQ modulator also, if you want to. So essentially what this just multiplies with a sine wave. I can put some small write-up on the Google Classroom and put it up today. So that will explain you all these details on how to do this subconversion. Okay. So on the receiver side, what happens? You have the same oscillator that gets multiplied. There's a small low pass filter. You get your I, you get your Q. Then you do modulation, constellation DMAC. So at this point, there will be an ADC, analog to digital converter. Okay, this will be fed into demodulator. Okay, so what does the demodulator do? I'll just tell you an example of how a demodulator works. So suppose you're transmitting the QPSK. Okay, so these are the 4 constellation points. Each of them will have some bit representation. This is 0, 0, this is 1, 0, 0, 1, and 1, 1, for example. Okay. Suppose you receive a point like this. Because of noise, what will happen? You transmitted this point, but you received this. Okay, because of noise. So the question is, what do you do? How do you find out what you transmitted? Then what you do is you find the nearest point. Nearest point is this. For whatever you have received. Okay? Once you get the nearest point will correspond to 0, 0. Okay, so you output 0, 0 here. So here output will be bits. Okay? So these bits will go into FEC decoder. Okay. And after the output of FEC decoder, output of FEC decoder can go to decompression or something. This is your messages. Effectively, this is your message. Okay, it can go to decompressor or something. If you don't have a decompressor, it's just your message. Okay. Is this receiver chain clear? I mean, at least the high level, it's clear.
Sir, what is LNA?
Low noise amplifier. Okay. So in the transmitter chain, we put power amplifier. On the receiver side, we put low noise amplifier. Okay, because the receiver chain, you don't want to add too much noise to the receiver signal. Okay. Okay.
Sir.
So let's talk about noise. This is the correct time to talk about noise.
Ganti sir, can I disturb you?
Please, sir, please.
Sir, here when after low noise amplifier, a complex number is coming, I and Q.
No,
in a
low noise
single.
amplifier. No. Remember, at this point, it's a signal, just one real signal. RF signal is a real signal.
Okay.
I and Q are two parts which we are interpreting as complex.
Okay.
This we are interpreting as complex, but they're known. So essentially, what is the I is passing through this, Q is passing through this. They are upconverted. So essentially, let me just write up the equation, maybe it will become clear. So what you do is, if you have I of t, which is the maybe real I in phase part, you multiply cos 2 pi fct minus Q of the quadrature part. Sine 2 pi fct. Okay, this is your transmitted signal y of t. So this is what your y of t is. Okay, y of t is a real signal. Okay, it's one signal. Does it make sense, Alex?
Yes, sir. Sir, before DAC, single wire is coming, right? So
Before DAC, two wires are coming. I just put I and Q. Two wires are coming. One for I, one for Q. There are two DACs. One for I, one for Q.
Got it. Thank you.
Okay. So at this point, you still get a real signal. So at this point, you still get a real signal, real RF signal. The same signal goes into both. Okay, one multiplies with cos, one multiplies with sine, and then you pass through LPF. Automatically, I and Q comes.
Sir, here just I want to ask you, sir, that in the receiver side, that your head modulator, that oscillator is there. Here you don't have the phase shift of 90 degrees. For
Yeah,
one of the
yes, sir. I have. I'm not drawing that. I didn't draw that here.
Okay.
What you said is absolutely true. So there's a sine wave that goes here, and there's a 90-degree phase shift.
Okay, thank you.
Yeah, you are absolutely right. I mean, I just didn't draw that. I was a little bit lazy. Yeah. So what I'm going to do is I'm going to, since there's some interest in this particular part, I'm going to put a small write-up or PPT in the about the up conversion and down conversion also, so that things become more clear. Okay, just give me a day or so. I'll just do that and put it on the classroom. Okay. So, but from the high level, one thing the few things that I wanted to take in mind. So, baseband is a complex number. That's the first thing I want you to think about. Baseband is a complex number. You have bits which come out of your FEC. You map to modulation. The modulation output is complex number which you transmit. Okay, which you do an IQ modulator and transmit. Similarly, on the receive side, you get a baseband signal which is a complex number, I and Q. So you can think of a complex number as I and Q, or you can think of this. So in general, what you do, how do you write I plus I times Q? This is square root minus 1. Okay, this is how a complex number is, x plus IY. Okay. So where does noise, what is noise? So where does noise gets added? Noise gets added everywhere. Anywhere there's an electronic component, noise gets added. But it turns out that most of the noise gets added at the beginning of the, at the antenna port. Okay, that's the fundamental place where noise gets added. Okay. So how much noise gets added? There's a formula called KT delta F. Okay. So what it means is K is something called the Boltzmann constant. I forget the number for the Boltzmann constant. Some 1.38 into 10 power minus 3. Let's not worry about that. Anyway, it doesn't make. T is the temperature, and delta F is your bandwidth. Okay. So in general, how we write it as, we write it in dBm. So the power of the noise that's get added in dBm is equal to minus 173.8 dBm plus 10 log 10 the frequency, the bandwidth in hertz. Okay, so this is the amount, this is the power of the noise that's get added into your system when you have a bandwidth. At least this much noise will get added. More than this can also get added if your electronics are good, but at least this much noise for sure will get added. If there is a 50 ohm resistor, this is the amount of noise that will surely get added. Okay, so if you look at this formula, it says that the noise that gets added is proportional to the temperature and the proportional to the bandwidth. So if you have a larger bandwidth signal, larger amount of noise gets added, because noise also is there for all the frequencies. So larger the amount of bandwidth you have, larger amount of noise gets added. For example, if you think about a 20 megahertz signal, 20 megahertz signal, okay, which is typically your Wi-Fi, the amount of noise that gets added is minus 101 dBm. This is your noise floor. This is also called noise floor. Okay, for a 80 megahertz signal, it is minus 95. And you can see now for 1 gigahertz signal, 1 gigahertz, this is bandwidth. This is not the center frequency, it's just the bandwidth. 1 gigahertz bandwidth, you get minus 84 dBm. Okay, so just remember these numbers. So I mean, I think it's important that we have an understanding of this formula. Let's not worry about how we derive this formula and other things that's there in physics. So from our side, if the amount of noise that get added, it depends on is proportional to the bandwidth. The amount of noise that get added is proportional to the bandwidth. I'm just going to take 5 more minutes.
So you have taken the temperature as some fixed value.
Fixed value, so 26 degrees, 300 Kelvin. 300 Kelvin, yeah.
Thank
you. So these computes are for 300 Kelvin. So this is for 300 Kelvin. I think approximately 26.
Are you talking about thermal noise?
This is thermal noise. This is thermal noise.
Okay.
This is also called additive white Gaussian. I'll tell you why this in a minute. Okay, that's what we are going to do. Okay. So let's not worry about the physics of this at this moment. Okay. So now what I want to do is I want to introduce a simple model. Okay? So now you have a transmitter like this, you have a receiver like this. Okay. See, if I start bothering about what happens in the electronics and all this, I mean, I will not be able to do any baseband processing or baseband algorithm. So what I do is I abstract it out. What I do is I don't worry about what happens from this point. Okay. Similarly, I don't worry about what happens at this point, up to this point. I abstract it out. What I say is, I write something like this. I do something like this. Very simple thing. I have my bits. I have my modulator. Okay, I have my modulator. At this point, I get INQ now. The INQ I get. I'm going to write it like fat. Okay? On the receiver side, after the ADC, what do I get? I get INQ. Okay, demodulator, and then goes to bits. Okay, so essentially this is message M. This is my message M hat. What I do is the first simplest channel that we are talking about is called 80 white Gaussian noise. Effectively, what we say is noise gets added here. Okay, so instead of worrying about what happens in the RF and other things, we make a simple model. This is the most important model. We make a simple model. We say that I am not worried about what happens in the RF and other things. I don't care, because anyway there's an up converter in the transmitter, there's a down converter in the receiver, and these two cancel each other. Effectively, what happens is noise gets added. Okay, so this is also a complex noise. Because you have INQ, which is a complex number, you add complex noise. So this model is called additive white Gaussian AWGN model. Okay, it's represented as Y is equal to X plus N. Y, X, and N are complex numbers. Okay, so X represents the output of your modulator, which is, can be BPSK, QPSK, 6 into M or something. Y represents the input to your demodulator, which is a corrupted version of what you transmitted here. So this is your X, this is your Y. N is modeled as a Gaussian noise. What that means is N has two components. N is equal to Ni plus NQ, a complex number. Ni is Gaussian distributed. It's Gaussian distributed with mean 0 and variance sigma square by 2. NQ is also a Gaussian noise which is distributed with 0 mean and sigma square by 2. And sigma square is nothing but KT delta F. Okay, in dBm or dB or whatever you want. Okay, so I'll stop at this point. There's too much to understand. So think about this particular model. I may go to come again next class. In the next class, what we are going to do is I'm going to tell you how do we use this AWGN model to obtain bit error rate curves. How do we simulate this AWGN model and obtain bit error rate curves? Okay. So any questions, or we can conclude the class today.
This is VK Roy, Professor. Good morning.
Good morning, sir. Please, sir.
Actually, this question is related to the measurement aspects of the noise. Whenever we increase the resolution bandwidth of a measuring instrument of any signal, that means the noise floor, the white noise, that will increase automatically in proportion with the bandwidth, I think.
Yes, that's the KT delta F.
Yeah. So actually, I was thinking about the measurement of EMF, in that the floor noise increases always when we increase the resolution bandwidth. Thank you, Professor. Thank you.
Yes, that's because of this delta F. Yeah,
Yeah.
that's what happens.
Certainly. Thank you.
I also have some general question, not about the content of the class. The document which you have put, it's opening in the browser. Can it be downloaded, or one has to read only onto the browser? That is one.
No,
Secondly,
the